And thank you, Darren and Bayan, for this invitation. So I just moved from University of Alabama to Indiana two months ago. But this is actually give me opportunity in what I want to do for years. So the first thing, try to survey the, oops. Yeah, so this is actually the work I have done when I was a PhD student back to the 2001. So at that time, I was trying to use the MEMS technology, to make a voice coil, microspeaker. So so this actually involved our silicon micromachining process, micromachining. So you etch in the cavity from the silicon, and also use electro deposition for the coil, as well as the soft magnet like a nickel iron. And by the end, we tried a couple of things, to make a permanent magnet based on the nickel ionized magnet, and then you etch in a couple hole. So on the top, these are showing the release structure of the speaker, and the circle in the middle, that's actually the voice coil. And then on the outside is actually surrounded by the soft magnet. And we actually at that time, tried different micromachining technique, try to make both a silicon nitride as well as a Perlin membrane. And this is actually the first, report, on the response for those kind of like electromagnetic speaker. So because I designed the resonant frequency around 3 kilohertz, because our audio voices range from the 20 to 20 kilohertz. So you want to cover a little bit higher pitch, so we can cover a lot longer. And then you got for the response, you can see the resonance also occur at the 3 kilohertz. And more exciting is, by the end, when I was a student, I just made those kind of a coupler, a small chamber of the volume to cubic centimeter, because at that time, there are the minic, coupler are quite expensive, and they are only sold by the company in Finland. So we have to make it our own. But what I learned from this process is my PhD advisor just joking, we are making a noise maker. It produces quite a lot of sound, but it's really higher frequency. And you can see actually, what couldn't really get achieved is actually the low bass sound, because this is an approach still very primitive, and then there's actually a lot of enclosure design I haven't paid attention to. But just very 2 years ago, I actually run to the some friends. Okay, so there are some interest to see if we can revisit, those kind of like a voice coil, microspeaker, and these are still very early stage phase. It's based on the same principle, I proposed, 25 years ago, and then, but they just do it much simpler, because it turned out, silicon micro machines are really expensive. So they do a lot of things. They're just doing the 3D printing, and then I actually heard the sound quality, it's actually quite good. But again, there's always a room to improve. So when you think about the micro speaker, because I think everybody is aware, there's a definitely some killer application, for the because Apple, AirPod become very popular, and back in the time, I was trying to do the micro speaker for the hearing aid application, and for the hearing aid, definitely want to get everything really, so they can put totally in in the ear canal, so it becomes very invisible. But again, I would say, currently, there are more desire to put more function in those kind of devices. As I talked to the several hearing aid company recently. So, but never to say, so MEMS microphone, already reached the allowed big scale, like $1.5 billion in 2020. They expect to grow, every 10%. But right now, the main speaker, the volume production are pretty low. In the end, I will give you some commercial company doing that. But there's actually a lot of hope, if we can, make this work, there's actually will be a lot of market value. So before I go through the further, for the review, let's talk about the white elephant, what are the challenge here, okay? But in the end, the size does matter, right? Because we have the sound wave audio sound, cover from 20 hertz to 20 kilohertz. That represent your wavelengths of the sound from 17 meter to 1.7 centimeter. Okay, and this is a physics you cannot change. Okay, and also if you want to produce more low frequency sound, so in the world we call this as a bass sound, right? And that actually with the size of volume, you basically just quasi equal wavelengths. So you cannot really get around of those kind of issue here. And so usually this is a very simple formula here. Basically the pressure is proportional to the membrane size, which is S, and also to the frequency square. So the divided by the distance. Okay, so if you are talking for the AirPod or hearing aids, this distance actually not relevant because you are talking to the very short distance. Okay, but definitely the challenge is how you can overcome this challenge between the sound loudness and the sound quality. So there's actually in the audio engineering, there's actually a famous called the Hoffman iron law. Okay, and basically this law just tells us you probably can optimize two conditions, two parameters, but you have to at the cost of sacrifice of third performance. Okay, so and this is just based on the physics. Okay, but what I want you to bring to your attention is actually the follows. Okay, because a lot of time we design those kind of piezoelectric micro speaker. We really focus on a lot on the like a quality factor, right? Resonance. Okay, but for the hearing aid, or the micro speaker application, this is actually not the one stone kill all the birds strategy. Okay, because for the different sound range, okay, you actually need a different requirement. Okay, so one thing pretty obvious is actually a quality factor, because a lot of main structure, they are built based on the resonator, and this resonator has a very high quality factor. But for the speaker application, that necessary is a good thing, because in particular for the low frequency, you vibrate a sound and then you want this to stop, so the other sound can get excitation. But right now, if you just come to the high resonant, high quality factor, you basically the sound was distorted because that resonance. So those kind of suspension system need to be taken into consideration. And also again the challenge is really low frequency. Okay, for this kind of low frequency, actually you actually kind of like a low quality factor in this range. But usually piezoelectric material, they are more stiff, okay, material. So you don't really achieve really high resonant, low resonant frequency at the baseline. Okay, and then at a higher frequency, you actually want a low bit damping of the speaker design, so they can basically get the stop easily. So So there's actually a lot of requirement, not just the resonator itself, okay? And finally, I want to say is there's actually, a lot of things need to be done, like acoustic enclosure, okay? Because that's the way you can generate highly quality sound, in particular at the low frequency. And actually, right now, there are actually a lot of paper right now pay attention to using the electronic, the filter. Basically, they can, modify the frequency response of the speaker, in the audio engineering, this is called the audio crossover. And so there's actually a lot of technique you can follow that. Sorry. So what's the advantage using the piezoelectric material? So first thing is actually quite simple, right? So they are very simple structure, and this piezoelectric material, they are usually more reliable, okay, for the and they have a very low power consumption, okay. This is actually contradict to the voice coil design, because you based on the Lorentz force, actuation, and a lot of time, the heating of the voice coil cannot be avoided, okay. So, but again, the acoustic performance are still moderate. So they don't necessarily produce a very high quality sound in the bass and the mid range. But on the other hand, right, we those kind of low cost piezoelectric material are very common, right, in the market where you just need a low cost and the high pitch sound, pretty is there. So, but if you talk to the certain manufacturer, what they really want to achieve come from the piezoelectric micro speaker is actually two things. The first one is a low driving voltage. Okay, because this day you still require like a 20 volts to drive the piezoelectric material as a speaker. Okay, to allow application, that's just too high. And the second is actually a lot of MEMS speaker these days, they are using the technology called digital sound reconstruction. So they actually the sound, audio sound are actually construct based on the really high pitch ultrasound. Then you basically using the signal processing to modulate, and there's actually a lot of uncertainty for the ultrasound sound to the human body. But nevertheless, okay, there's actually a paper recently, just try to define what's a figure of mermaid for the micro speaker. I would say this still not really represent the whole picture, because these figure of mermaid are based on the really simple cantilever structure, and then basically what you just say you just try to reduce the thicknesses of the piezoelectric materials to get a better performance, okay? But nevertheless, okay, there are some, piezoelectric material you actually can use, okay? MEMS use a PCT material, but many are working on the aluminum nitride and also the scanning dope aluminum nitride. And there are some using the piezoelectric polymer like a PVDF. Okay, so I'm going to give some like from a history point of view, for this field. So the first, piezoelectric micro speaker you probably find, come back to the 1996, back to the Berkeley day, where Professor Lee, they're using the cantilever depth, okay, and where the piezoelectric material at that time, because at that time the PCT and aluminum nitride doesn't really exist, so they use a sparkler, zinc oxide as a piezoelectric material. They put on the edge, because by the end, right, we are and then using the cantilever structure try to amplify that vibration, okay, and because this cantilever need to vibrate, so they have to cut the release the structure as a cantilever. That kind of called the free edges, and this is actually the the response, they got couple of years later. Okay, so these pressure, are still very low. Okay, because for the audio sound, right? Because our human, normal sound around the 80 to 90. Actually, when you are whispering the sound, that can be 60 to 80 psi. Okay, but for a lot of hearing aid application, a lot of time you even want to go to the 100 SPL. Okay, so that's actually much larger. And then the Professor King at USC, he basically just put a zinc oxide piezoelectric material on the membrane, and he started with a silicon nitride, and then later on using the kaolin, as a membrane structure. So those are kind of response you can get. So again, you can see the low bass sound still lost a lot. That just basically 40 decibel until you hit the higher resonance. And this is actually a recent paper. So in this idea, they basically just put the polymer, okay, as a vibration structure, but it's a polymer actually by the PCT. So it's a little bit complicated silicon micro machining process, but in the end, they can get the resonance, around also the 3 kilohertz, and that you actually can get the really high sound, loud sound, if you're driving the higher voltage. So for them, it's a 15 volt plus a 6 volt AC, and this device actually, will get a better sound when you couple with a small volume like a 2cc coupler. So here, you still get the almost 100, but for the hearing aid, you really want to get a flat response for those kind of application. So I think MEMS, so all of a sudden you don't hear a lot on the micro speaker until a couple of years ago, they published this paper, okay, from Germany. So they plan, you basically using the piezoelectric material, and then you basically just cut the edge around the center. Okay, so they call this as a cantilever, membrane. So this is actually, really very similar structure, back to the 1996, except the shape, at that time was, the square, but right now it become more like a triangle. Okay, but they actually introduced a really two very interesting concept. Okay, the first one is actually they are driving the actuator, at a different steam, because back in the time you only have one actuator, and now since if you are able to have the 4 different electrode, and then you can drive the all phase one side, so you got to basically double the amplitude of the driving. The second is actually they put finally somebody put the filter in the system. Okay, so you can see the raw response of the speaker was the dash black line. Okay, which is you got a spike at 10 kilohertz. But if you add the low pass, a filter, so you basically can get a little bit flatter response, for the speaker location. Of course, you have to drive the almost higher voltage to be able to meet the higher sound, and that's actually something still quite challenging. So if you cut in the air vent in the structure, there's always questioning what does the air vent is doing. So there are a couple of the paper recently try to seal in those kind of vent material using the polymer such as PDMS, kaolin, and others. Okay, so for this paper, specifically, they just put a PDMS drop, along the edges, and this capillary sealing, finally just seal the structure. And what you can see the improvement is actually, something like, at a low frequency, you see a little bit increases from the blue line to the orange line. And the higher frequency, actually is a little bit, so there's actually not very clear, what is the how much you can tell, with those kind of seating structure. Okay. So another thing which is a Professor Feng from National Tsinghua University trying to do is that he's a micro machining person. So he's basically, adding the more structure, okay, in the resonance structure. So instead of the membrane or the diaphragm, right now you can couple with some mechanical structure that introduce a different resonant frequency, and then when they couple together, you are hoping to get a good response, for the speaker. But again, if you look at what they are end up measuring, those coupling are still too strong. So you definitely, there's a lot of design need to be think about. And they also propose the different driving speed. So you, instead of just one electrode, they use a multiple 3 or 4 to try to improve that vibration power as well. So this is a paper from the same group back in 2018. So this is actually interesting because right now they are paying attention to the acoustic enclosure. So here they actually still the piezoelectric can deliver a membrane that's vibration on one end, but on the back you actually put a lot of SUA host, and this actually serves a couple of purposes. The first one, you are actually increasing the volume of the enclosure, and those kind of enclosure actually will help, because basically when you have a membrane vibrate and at a low base, the radiation from the front and the variation from the back, they are 180 phase different, so they will cancel each other. So you you actually need some like a acoustic design, try to absorb that reflected sound. And this is the one thing they come with a console simulation and the optimized structure. And again, they also put a filter, so you can get a really flat response. But this is still like below the 90 dB SPL. So there's a lot of things you want to improve that to the higher sound decibel. But so those are the pretty common MEMS type of the micro speaker. But there are actually a lot of things happening also that's simple. Because PVDF, although so far we don't introduce any design, but they are actually gradually a lot of people are using that for the flat display speaker. Okay, so you want to have a speaker that will come from your monitor, so to speak. So and they put a polymer, which is a PVDF, the sandwich between the transparent electrode, like ITO, and they can measure the sound. So for this application, it's actually for the loudspeaker, and you actually have those kind of response, from, and you have to try the very high voltage. Usually they try 100 volt. So this is definitely something need to be happening. And if you can use a material, right? So there's actually a lot of a couple of years ago, can we use the graphene? Because the graphene, it turned out, it's a really thin material, and it's actually very mechanical robust. So how about you drop in the graphene? Okay, but the graphene is not piezoelectric material. Okay, so but you can use it as like a flat electrode. So So in this paper, they just using the electrostatic force. Okay, so they driving the pretty high voltage, because usually the electrostatic force actuation for the micro, you have to go to the almost 30 volt to 100 volt. So that's still kind of like a challenge here. And finally, this is something I know just thinking back, right? So what do they use current for the heating aids? It's actually very simple, balanced armature microspeaker. So those are the technology has been exist for more than I would say 50 years. Okay, so and basically it would be a coil which is an end around the armature. Basically, it's a cantilever pin. Okay, and this armature in the front got the two magnet. Okay, so if you are actually apply the current to the coil, then you will magnetize the cantilever, and this cantilever will move up and down, because of the field. And in the front, there's actually a driving pin, which attached to the membrane, and then you can move the membrane up and down. Okay, so really amazing, those are really sophisticated machine. These days, the node cell, miniaturized, almost a 5 millimeter times a 2.7 times a 3.9. This is almost so there are actually a couple of the company try to commercial this. Okay, so the first one is the audio pixel. Okay, so this audio pixel, they are based on electrostatic actuation. So they basically make function of the pixel array, and the idea is based on the digital construction. So you don't produce an analog sound, but instead you produce a lot of pulses. So you are modulate each pixel, so they have the different phase, and in the end, they superposition to the audio wavelengths that you need. And this company has been exist for 20 years, okay? But so far, there's no real product, okay? Ouyang is actually, you can find a lot of Ouyang product on the digital key. So I would say, Ouyang credit for that, their design is actually piezoelectric material. So those are the piezoelectric material, the post attached to the membrane. And then, you are vibrate, when you apply the piezoelectric. So this is they are funding, 2012. You can actually buy them. Okay. And finally, I think this is a MEMS, right? They are actually allowed to talk on MEMS devices. And I would say, they can take, they do get a little bit smaller, right? But again, they are based on the piezoelectric, and they have to use in the digital sound construction. But again, they give a lot of hope. I think I will probably just stop here because the time is up. Thank you.